In this video, we are going to take a look at gas stoichiometry. Please read the OER textbook chapter section 9.6 for more detail and start your homework as soon as you finish watching the video. In this chapter section, we are going to utilize the mole that is part of the PV equal nRT to use as mole-to-mole ratio to allow us to do some conversion. For example, go from mole of something, right? So mole of gas A to mole of gas B, for example, right, within that chemical reaction, or you can do like mole to grams conversion as well, or mole to molecules conversion as well, right? So my expectation is you will need to be able to convert all of these based on the mole-to-mole ratio when we are looking at the chemical reaction. This gas stoichiometry is going to be very similar to the chemical stoichiometry that we cover in chapter 7 in Chem 121. Okay, so if you don't remember that, you need to recall Chem 121. Okay, so let's take a look at this real quick. So this is what I'm talking about earlier. So this stoichiometry roadmap here, this is what we learned in Chem 121. Okay, so this whole thing right here, this is what we learned in Chem 121. If you don't remember it all, you need to go back and then refresh your memory on those. Okay, so pretty much in Chem 121, you learn how to convert from grams to mole, right? Using molar mass. You also learn as well, if you are given a chemical reaction, you can use mole-to-mole ratio to convert from mole of A, right, to mole of B, for example, or mole of molecule A to mole of molecule B and things like that. Okay, so you can also use Avogadro's number to actually find out the number of molecules as well, right? And if you know the chemical formula, you can use the ratio within the chemical formula to help you to find out the number of atoms within the molecule as well. So we cover all of this in Chem 121. Okay, so pretty much Chem 122, what is going to be in addition to that is going to be this part right here. Right, so chapter 8, we already see the joule, right? So every time when you see joule per mole, we know that that is per mole is going to tie back into the stoichiometry as well, right? So it's going to be able to give you feed into this stoichiometry roadmap as well, right? So as you know joule, you should be able to find out the heat that associated with that reaction as well. So this is what we cover in chapter 8. Okay, so now this chapter 9, what we are going to use is we're going to use PIVNERD to help us fit into this stoichiometry roadmap. Okay, so that means in this case, this mole right here going to fit into this mole. And if you know more, then you should be able to convert to any of this. Okay, so you can go into any of this direction. Okay, so that's going to be our goal here. Okay, so same thing as well, right? For a different mole of gas, you can still use PIVNERD as well. Now let's take a look at example. Okay, so that way you understand that better. Okay, so in this reaction, we are going to look at the decomposition of silver oxide that generates silver and eventually oxygen gas as well. Okay, so it said that if 4.58 liter of oxygen, okay, so this is giving you the volume of oxygen, right, are formed at this pressure and at this temperature, is asking you how many grams of silver oxide going to decompose. Okay, so asking you grams of silver oxide that is going to be decomposed. Okay, note this. Okay, so you can put this in your note card as well. Okay, so this is very important. The PIVNERD, PV equal nRT equation, can only be used for gas. So that means if you plug in all this given value, okay, if you plug all this given value in and you calculate for n, right? So if you get an n, note that this n is going to be n of gas. Okay, it's not going to be n of solid. It's not going to be n of liquid. Therefore, in this case, if you plug all this in, the n value or the number of mole that come out is not going to be the number of mole of silver oxide. Okay, because the silver oxide is solid. Okay, so that means in this case, it's very crucial that you understand this. This N right here is going to belong to oxygen, right? Because it's the only thing that we have as the gas is the oxygen. Therefore, in this case, the idea is that you need to use the mole of oxygen eventually to convert to mole eventually of silver oxide. Okay, so how do you do that? Well, if you go back to this, right? If you go back to this roadmap right here, if you know more of something, you can find out more of something else by using the mole ratio. So therefore, in this case, if you go back here, right, it makes sense. Now, if you use PIVNERD to find out N of oxygen, then you should be able to find out N of silver oxide as well, because you know the mole ratio here, right? So then if you know more of silver oxide, then you can convert to grams of silver oxide. But the key word is PV equal nRT can only be used for gas only, not liquid, not solid. Okay, so you need to jot this down. So now in this case, again, so I'm gonna plug that into the stoichiometry roadmap that we learned earlier. So you are going to use PIVNER to get the mole of A. So in this case, it's gonna be oxygen, right? And then you are going to use the mole ratio to get to mole of B. So in this case, it's gonna be silver oxide. Okay, so after you get more of B, then you can find out the grams of B or silver oxide in this case by using silver oxide molar mass. Okay, so that's gonna be our plan here. All right, now let's us actually calculate for this. Okay, so I'm going to go ahead. So I'm gonna rearrange this. Okay, so I'm gonna get N equal to PV over RT. Okay, so I'm going to plug in the pressure value, but you need to convert this into ATM first. Okay, so I'm going to convert this into ATM, 1 ATM. Okay, so that is going to come out equal to 0.9803 ATM. Okay, so, and then in this case, I'm going to plug it in 0.9803 ATM, and then volume is 4.58 liter divided by R 0.0821 ATM liter mole Kelvin, and then temperature is 308 Kelvin. Okay, if you do this correctly, you are going to get N to come out to be 0.1775. Okay, so I'm just gonna leave it like this. Okay, so this is more of what? Again, we are looking at oxygen, right? This is gonna be more of oxygen. Okay, so I want you to jot that down. So this is gonna be more of oxygen. Okay, so the next thing that I'm going to do is that, well, we already have more of oxygen. Okay, so this is gonna be more of oxygen right here. So the next thing is I'm going to convert more of oxygen, okay, 0.1775 mole of oxygen to mole of silver oxide. Okay, so this is going to be mole of silver oxide. This is mole of oxygen. And as you see, the reaction right here is giving us 2 to 1, right? So every 2 mole of silver oxide is going to generate 1 mole of oxygen. Okay. The next thing, so if you're looking at unit, right? So this unit cancel out, you have more of silver oxide left. So the next thing is going to be more of silver oxide, right? Per grams of silver oxide. Okay, so in this case, you need to use the molar mass. So in this case, if you add them correctly, the molar mass of silver oxide would come out equal to 231.74 grams. Okay, so in this case, if you cancel the unit, okay, so you're gonna have the grams of silver oxide left, which is exactly what we want, right? So now all you need to do is you are going to multiply all the top number and then divide by the bottom number. So if you do that correctly, you are going to get 82.3 grams of silver oxide. Okay, so this would be your answer. So again, so this problem contains 3 sig fig, so your final answer gonna come out with 3 sig fig as well. All right, the next one, I would like you to actually doing this yourself. Okay, so let's pause the video and then complete 1B yourself and then resume it again when you finish. Okay, let's check your work together. Okay, so 1B, okay, so asking you how many milliliter of oxygen. Okay, this is giving you pressure, this is giving you temperature, and I'm just gonna convert this temperature into Kelvin right away. So it's gonna come out to be 298 Kelvin. Okay. Pressure, I'm going to convert this into millimeter, ATM right away, but divide by 760, right? So in this case, 734, you are going to get 0.9658 ATM. I'm not going to round it yet, so that's why I keep those 4 sig fig. Okay, so eventually you're going to have it only 3 in 3 sig fig. Okay, but I'm just going to keep it all so that way we don't round the error. Okay. So in this case, it's asking you to find out volume of oxygen. It's giving you pressure and temperature, but we don't know the number of mole yet. So therefore, in this case, you need to first find out mole of oxygen in order to plug it in here, right? So without knowing mole, you're not going to be able to find out the volume. Okay, so in this case, you will need to find out number of mole of oxygen first. And what else given to us? Well, it's giving us grams of silver oxide instead, right? So in this case, what you are given is you are given grams of silver oxide. So that means you, in this case, you will need to convert to mole of silver oxide first, right? And then use mole ratio to convert to mole of oxygen. And then you can use Pfeffner to get the volume of gas. Okay, so that's going to be the idea or the route that we are going to take for this problem. So what I'm going to do is I'm going to set up mole conversion first. So 7.9 grams of silver oxide. And we know that every 231.74 grams of silver oxide equal to 1 mole of silver oxide. Okay. And according to the equation here, we know that every 2 mole of silver oxide is going to produce 1 mole of oxygen. Okay. So far, if you get into this step right here, you are going to get 0.015297. Okay, so this is mole of oxygen. Okay, this is not the final answer because it's asking you in liter. So the next step is plugging this into the PV equal nRT. I'm going to rearrange this equation. Okay, so I'm gonna get V equal to nRT over P, right? So if I do that, I'm going to get V equal to N is 0.015297 mole. R is 0.0821 atm liter mole times Kelvin. And then temperature is 298 Kelvin. Okay, divide by pressure, which is 0.9658 atm. Okay, if you do this correctly, you are going to get volume of oxygen come out to be 0.3875 liter, but it's asking for milliliter. So we're gonna have to do one more step. Every 1 liter equal to 1,000 milliliter. So in this case, you are going to get 387 milliliter, okay, or 388, right? Because you are rounding one up. Okay, so in this case, your final answer should come out with 366. So this would be your final answer for B. All right, so I would like you to do the same thing for number 2. I would like you to go ahead, finish number 2 and then resume the video again. Okay, so pause the video now and then start to work on number 2. And there is the follow-up question as well. Okay, so asking you how many milliliter of CO2 that can be produced at this condition. Okay, so let's go ahead, pause the video and then complete number 2 and then we can check answer again together. All right, so let's take a look at your work. Okay, so in this case, it's giving you the mass of citric acid and also mass of sodium bicarbonate as well. And it's asking for mole of carbon dioxide. Okay, so this is what it's asking, mole of CO2. Okay, so now the question is, how do I know which one is citric acid? Well, remember it said citric acid react, right, with sodium bicarbonate. So that means in this case, one of these two are gonna be citric acid because they react together. If you don't know citric acid, at least you need to know sodium bicarbonate, right? Because we learn about the naming of any compound, which is part of Chem 121. Okay, so in this case, sodium, right? So it's obvious, it's right there, bicarbonate. Okay, so this is contain carbonate, right? So ions. So that means in this case, the sodium bicarbonate is going to be this species right here, right? And this would be the citric acid. Okay, so that's how I know. Okay, so now wait a second, it's giving us mass of both. We know mass of these two. Why is giving us both of them then, and how do I do this, right? So again, recall from 121, okay, when you are given two information of the reactant, okay, so this is going to be when you need to find the limiting reactant, which one is going to be all consumed first, right? Because that species that is the limiting reactant is going to limit the amount of the product that can be made. So in this case, if you know which one is the limiting reactant, then you know that the same that is going to limit the amount of CO2 that is going to be produced. Okay, so that means in this case, what you are going to do first, you are going to need to find out their molar mass first, right? Because you need to convert all of this mass into mole. Okay, so in this case, you will need to go ahead, calculate for molar mass. So these are the molar mass of all of that. Okay, so I'm gonna calculate for all of it. Okay, so in this case, what we are going to use now, I'm going to use the molar mass of these two, okay, because we are given mass of citric acid and sodium bicarbonate. Okay, so I'm gonna go ahead, actually calculate for the amount of CO2 that is being produced. Okay, so I'm going to first set up with citric acid. Okay, so we have 1,000 milligrams of citric acid. And I'm going to convert these milligrams to grams first. After I get grams, then I'm going to use molar mass of citric acid, right, to convert to its mole. Okay, so 192.124 grams equal to 1 mole. This is still of citric acid. And then what I'm going to do next is I'm going to use the ratio, right? So we see that this is the citric acid right here. Every 1 mole of citric acid is going to produce 3 mole of CO2. I'm going to get that. Okay, so what is the final answer? So if you calculate, you multiply the top number and then divide by the bottom number. If you do this correctly, you are going to get 0.0156 mole of CO2. Okay, so this CO2 is the amount of carbon dioxide that can be made from citric acid. Okay, now we're gonna check the same thing with sodium bicarbonate. Okay, so I'm gonna do 1,916 milligrams of sodium bicarbonate, and I'm going to again convert these milligrams to grams, and then use molar mass of sodium bicarbonate to convert to its mole. And then I'm going to use mole ratio, right, of the sodium bicarbonate and carbon dioxide to get to mole of carbon dioxide. Okay, so 3 mole of sodium bicarbonate produce 3 mole of CO2. If you do this correctly, you are going to get 0.0228 mole of CO2. As you can see, the amount of citric acid that we have per amount of sodium bicarbonate that we have, the only mole of CO2 that can be produced would be this much, right? Because it's going to be limited by the amount of citric acid. Okay, so therefore in this case, citric acid is the limiting reactant. This amount of citric acid limit that you can produce only 0.0156 mole of CO2. Okay, so this is what we refer to theoretical yield. Okay, so this is the maximum amount possible that you can produce. You cannot make 0.0228 because you don't have enough citric acid. Okay, so in this case, only 0.0156 mole of CO2 can be produced. So to answer this question number 2, the first part, how many mole of CO2 can be produced, is going to be this much. Okay, so this would be the answer. Now the follow-up question asking you, how many milliliter of this carbon dioxide gas then? Well, what you are going to do is, because we are looking at gas, right? This is gas, keyword is gas. Therefore, you can use PV equal nRT to help you find out volume. Okay, so again, the reason for that is because we are dealing with gas. Okay, so in order to find out volume, you are going to rearrange this equation real quick. So you're gonna get nRT over P. Okay, so because we know that the mole that we calculated earlier is only possible, only 0.0156 mole. Okay, so we're gonna use that. You're gonna multiply that by the R constant, 0.0821 ATMs times liter over mole over Kelvin. And then temperature is given as standard temperature and pressure. Standard temperature is 273 Kelvin. Okay, so pressure is at 1 ATM pressure. Okay, so the volume going to come out equal to 0.3496. Okay, so in this, this is liter, but this problem asking us in milliliter. So you are going to do one more step here. So every 1 liter equal to 1,000 milliliter. So you're gonna get 349.6 milliliter. Okay, so in this case, the number of sig fig is going to be limited by the R value, right? So this is 3 sig fig right here. This is also 3 sig fig as well. So therefore, in this case, we are going to round this up. So the final answer would come out to be 350 milliliter. Okay, so this would be your final answer. Here are more problems that you can do. Okay, so I would like you to practice this and then check your work against the answer key that will be provided on Moodle. Okay, so one thing I would like you to correct though is the this thing right here. Can you cross out 27 ml of 3.5 m? Okay, cross this out. The reason for that is because you have not learned the molar unit yet. That is going to be in part of chapter 11. Okay, so I don't want, I would like to avoid the confusion. What I would like you to do instead is that I would like you to change this sentence into if sulfuric acid, right? So this is if, okay, so if sulfuric acid was spilled, what is the minimum mass in grams of sodium bicarbonate that must be added to the spill to neutralize the acid in order to form 235 milliliter of CO2 at standard pressure, temperature and pressure. Okay, so I would like you to add this instead at the end. Okay, so in order to generate this, how many grams of sodium bicarb you need to add? That's what it's asking you, right? So is in order to generate this carbon dioxide, how many grams of this that you will need to add? Okay, so that's what it's asking you. Okay. Right. So here's a summary of chapter 9.6. Okay, so pretty much we are looking at gas stoichiometry by you are feeding this mole from the PV equal nRT into the mole of the gas, right? And then you can use the mole ratio to go to do several type of conversion. Okay. You should start working on your homework soon to practice this concept. Okay, so start working on chapter homework 9.6. And if you have any question, please do not hesitate to reach out to me during office hour.